In this video, we are going to learn about the spanning trees and their special cases, that is the minimum spanning tree in graph theory. Firstly, we will cover the spanning tree. After that, we will cover the minimum spanning tree with the example. And then we will move towards the algorithms, that is the Prim's and the Kruskal algorithms. They are used to find the minimum spanning tree. Now, what do you mean by spanning tree? Suppose we have the graph G, that is a simple and a connected graph. A spanning tree of the graph is basically a subgraph that includes these two properties. The first property is the tree must contain every vertex of the graph G and it should be a tree. Tree means it is connected and containing no cycle. Let's understand this by an example. Now we need to extract the spanning tree from this graph. Now what is the approach to find that spanning tree? We will ensure that all the vertices are the part of a tree and the tree is connected. Then we remove edges from the cycle. Like in this case, A is connected with B, B is connected to C, C is connected to D, and D is connected to E. So we are getting a cycle in this case of the length 4. So try to remove this cycle and make sure the graph is connected. So how we can remove this one? So we can remove this edge A to D. So we are taking a vertex A and B by an edge. Then B is connected to the C vertex. C is connected to the D vertex. Now the point is, can we include this edge as a part of a spanning tree? No, because it is also creating a cycle of the length 3. Now whether every vertex is a part of the tree? No, because E and F is not there. So we need to include these vertices as a part of this tree. So we have two options to include the vertex E by this edge BE or CE. So either we can take B to E edge or C to E. So right now I have taken an edge C to E. But we cannot include this edge because it is forming a cycle of the length 3. To include a vertex F, we need to take this edge because the tree must be connected. Now this covers each and every vertex of this graph and it is a tree. It is a connected and containing no cycle. So we call it as the spanning tree. Here we have the important result. Result is a simple graph is connected if and only if it has a spanning tree. This means if the graph is connected as well as a simple, then we can always find a spanning tree. Or if the spanning tree exists, the graph must be connected. Now moving towards the minimum spanning tree. So before moving to the definition of minimum spanning tree, we just need the term weighted graph. Weighted graph means a graph in which every edge is assigned a non-negative real number is called weighted graph. And that non-negative real number is called as the weight. For example, this is a weighted graph. Why it is a weighted graph? Because a non-negative real number is assigned to each and every edge. And this is called as a weight. Like A and B has a weight 2. B and C edge has a weight 3. D to C edge has a weight 1. A to D edge has a weight 4. Note that it is not necessary to take a different weight on the edges. Maybe we have a case that two edges have same weight. Now moving towards the definition of minimum spanning tree. Suppose we have connected weighted graph, a spanning tree that has the smallest possible sum of the weights on its edges, that is called as a minimum spanning tree. Means first we need to find the spanning tree. After that, we will calculate the total weight by just taking the sum of weight on the edges, and in which spanning tree we will get a minimum weight, that is called as a minimum spanning tree. Let's understand by an example. We need to find the minimum spanning tree of this graph. So first we will find all the spanning tree for this case. Spanning tree means we need to take each and every vertex as a part of a tree, or we can say that there is a no circuit in a graph. So in this case, the first spanning tree we can take it as A to B, B to C and C to D. It contains every vertex of the graph and there is a no simple circuit, so it is a tree. Another possible tree is we can take an edge A to D, D to C, C to B. Another possible case is we can take A to B edge, A to D edge and D to C edge. Another spanning tree we can take from here as D to A edge, then A to B and B to C. What are the weights over these edges? That is 2, 3, 1. So overall weight for this graph is 2 plus 3 plus 1, that is 6. For this spanning tree, 2, 4, 1. Overall weight is 7. For this case, 4, 1, 3. Overall weight is 8. And for the last one, the weight is 4, 2, 3. Overall weight is 9. Now identify a spanning tree with overall weight as a minimum as possible. That is a 6. In the first spanning tree, we are getting a minimum weight. So we call this graph as the minimum spanning tree of the given graph. As the total weight we are getting as a 6, that is minimum as compared to all other spanning trees. Now recently we have learned how to find the spanning tree, even a minimum spanning tree, by checking different combination. But there is a problem. As the number of vertices or edges increases, means the number of possible spanning tree grow very fast. So it becomes impossible to check each one manually. Imagine a graph with a 10 or a 20 vertices. We cannot draw all spanning tree and compare their weights one by one. That's where the algorithms help us. So algorithm like Prim's algorithm and the Kruskal algorithms gives us step-by-step method to find the minimum spanning tree quickly and correctly. And they save time, reduce mistakes and work on the large graph easily, even when there are hundreds of vertices and the edges. So let's learn how to apply the Prim's algorithm and the Kruskal algorithm to find the minimum spanning tree in a graph. Next, we are going to learn about the Prim's algorithm. It is used to find the minimum spanning tree. This algorithm was originally discovered in 1930 by the Czech mathematician Wojciech Jernik, and it was rediscovered in 1957 by the Robert Prims, due to which nowadays it is called as a Prim's algorithm and sometimes it is referred as Prim-Jernik algorithm. What to do in this algorithm? We will start with any arbitrary vertex in the graph. After that, we will pick the smallest weighted edge that is connected to this vertex, and we will repeat this procedure by taking the next smallest edge that is connected to existing vertices in the tree by making sure that it does not form any cycle while adding an edge. We will repeat this step till the time there are n minus 1 edges in a tree where n represents the number of vertices. Now let's understand how to apply this algorithm by using an example. Here, by using Prim's algorithm, we need to find the minimum spanning tree in a weighted graph shown in the following figure. Now, how to start the Prim's algorithm in this case? The first step, we can choose any arbitrary vertex from this graph. Let's suppose we have chosen a vertex A as a part of a spanning tree. Now check all the outgoing edges from this vertex A and draw by the dotted lines. So A is connected with B vertex, with D vertex, with C vertex. After that, we will pick the first edge by taking the smallest weight over these three ones. The smallest weight is 10. It means the first choice of an edge in a spanning tree is A to D with weight 10. So we will mention this one by creating a table. So first choice we have made an edge, that is A to D with weight 10. Repeat the same procedure. We have new vertex in a tree, that is the D. Now D is connected with vertex B, G, H and C. Also write the weight over this dotted edges. Now next we need to take the minimum weighted edge over the dotted lines. Here we have the 17, 14, 3, 6, 12 and 1. Minimum weight over the dotted edges is 1. So it means our next choice in this case is an edge B to D with the weight 1. So next vertex we have taken in our tree is B. Now B is connected with the vertex H, E and F with the weight 5, 7, 2. Repeat the same procedure over the dotted edges. Find the minimum weight. Here has 17, 14, 3, 12, 6, 5, 7, 2. Minimum weight is 2. So next choice we have the edge B to F with weight 2. It means the new vertex we have taken in a tree is F. Next, check all the outgoing edges from the vertex F, that is F to E and F to H with the weight 10 and 5 respectively. Now choose the minimum weighted edge over the dotted lines. Here we have 17, 12, 14, 3, 6, 5, 7, 10, 5. So minimum weight in this case we have on the edge D to G, that is 3. So next choice we have an edge D to G with weight 3. After including vertex G as a part of a spanning tree, check all the outgoing edges from the vertex G, that is G to C and G to H. Now find the minimum weighted edge over the dotted lines. 12, 14, 17, 12, 5, 6, 8, 7, 10, 5. Minimum weight is 5 and it is over the edge B to H and F to H. We can pick any one as a next choice. So the next choice we are taking in this case is, suppose an edge B to H with the weight 5. Now H is connected with G, D, F and with E by the weight 9. Now minimum weight over the dotted edges is again 5. Now think, can we include FH as a part of tree? No. Why not? Because if we are including this edge here, it is creating a cycle. And cycle cannot be a part of a tree, due to which we will discard this edge. So we will not include FH as a part of the spanning tree. Next minimum weight we have in this case is 6, that is from D to H. Can we take this H as a part of spanning tree? No, because it is again creating a circuit. So discard this H. Next minimum weight we have 7. Can we include this H as a part of spanning tree? Yes, because it is not creating a circuit. So the next choice we have an edge B to E with weight 7. Now next minimum weight we have 8, but we cannot take as a part of spanning tree because it is creating a cycle of the length 4, that is G, D, B, H, G. So discard this H. Next minimum weight we have 9. Again we cannot take this as a part of spanning tree because it is creating a circuit. Next weight we have 10 between E and F. So discard this because it is creating a circuit. Next minimum weight we have 12. One is between A to B, another is C to G. If we are including an edge A to B, it is creating a circuit. Again we can discard this. Can we include an edge CG? Yes, because it is not creating a circuit. Our seventh choice in this case is an edge CG with the weight 12. Now think whether every vertex is a part of a spanning tree. Yes. So we have included each and every vertex as a part of spanning tree, and with this we have the 7 choices as the vertices are 8. By this we are getting a minimum spanning tree. We just need to find the overall weight. So add these numbers and you will get the minimum weighted spanning tree weight, that is 40. So it is a spanning tree with the weight 40. So this is how the Prim's algorithms work. So the next algorithm we have the Kruskal's algorithm, and it is also used to find the minimum spanning tree. And it is discovered by the Joseph Kruskal in 1956. The concept behind is very simple. How to find the minimum spanning tree by using a Kruskal algorithm? The first step is sort all the edges in a non-decreasing order of their weight. Non-decreasing order means it is in a either increasing plus constant form. Second step is then we will pick the edge with the smallest weight. We will include it in a spanning tree if it does not form any cycle in that case. And the third step is we will repeat the same step 2 by picking the smallest edge and including in a spanning tree if it is not forming a cycle until all the vertices are not the part of a spanning tree. Let's understand how the Kruskal algorithm works with the help of example. So here we need to apply the Kruskal algorithm on the same graph and find the minimum spanning tree. The first step is sort all these edges in a non-decreasing order. So here I have sorted all the edges according to the weight. The minimum weight we have 1, then weight is 2, then weight is 3. After that we are not getting a weight 4 but we are getting a weight 5 over the edge B, H, F, H, and then the weight is 6 between D and H. Then the weight is 7, 8, 9, 10 2 times, 12 2 times, then 14 and then 17. This is the step number 1. The second step is we will take the first edge as a part of spanning tree because it contains the minimum weight. So the first choice we have in this case is an edge BD with the weight 1. So we can write choice edge and then weight. And also we can take this edge B to D. Next, can we take the next choice BF with a weight 2? Yes, because it is not creating any cycle here. And the weight over this case is 2. So our next choice is an edge BF with the weight 2. Can we include an edge GD with the weight 3 as a part of spanning tree? Yes, because it is again not creating any circuit. So the third choice we have in this case is an HGD with the weight 3. Now can we include an HBH? Yes, because it is again not creating any circuit. And the weight in this case we are having 5. So fourth choice we have an HBH with the weight 5. Next, can we include FH as a part of spanning tree? No, because it is forming a cycle, so discard this. Can we take the next choice as DH? No, because again it is creating a cycle, so discard this. Can we take an HBE? Yes, because it is not creating any cycle. And the weight over here is 7. So fifth choice we have an HBE with the weight 7. Now can we include GH? No, because it is again creating a circuit. EH? No. EF? No. AD? Yes, because it is not forming a cycle. So we can take the next choice as an HAD as a part of spanning tree. Can we include an HAB? No, because it is forming a cycle. CG? Yes. So we can take this H as a part of spanning tree and the weight in this case we have 12. So the seventh choice we have made in this case is CG with the weight 12. Now can we include CD? No, because it is creating a circuit. Can we include AC? No. Again it is forming a circle. Also we can observe that we are getting a tree that contains every vertex of this graph. Total number of vertices are 8 and we need to make the choices till 1 minus of the vertices, that is 7. So the total weight of the spanning tree is again 40. So either apply the Prim's algorithm or the Kruskal algorithm, we will get a minimum spanning tree with the same weight. So the difference between the Prim's algorithm and the Kruskal algorithm is, in the Kruskal algorithm, first step is we are sorting the edges and accordingly we are making the choice. Whereas in the Prim's algorithm, we can start with any one vertex and accordingly we will choose the minimum weighted edge. We will include that edge if it is not forming a cycle. So this is how these two different algorithms works to find the minimum spanning tree.